So our main goal here, we are going to start with what is a cache memory, the element of cache design. Hopefully, we're also going to talk about the logical cache organization. Now, it depends where we reach. I don't think we're going to reach the algorithm section, but if we reach, that would be good. Well, that's the replacement algorithm we're going to discuss. And then the right and also inclusion policies. So first we start with what is a cache. Well, in short, I would say cache is a memory, or the term we should use, the fast and small memory that we can store a data. Normally, we're going to use the cache instead of main memory because of the latency or the access time. So the access time for caches are more faster than the main memory. So that's a good term they use here also. It's like the buffer between CPU and main memory. So it's in the middle. So yeah, so that's all we can see. So as we said, this lecture will introduce us to again cache memory. Most important, the principles, design elements, as we mentioned, addressing organization, also the policies, mostly the right. So in short, I can say that the cache memory is designed to combine both the memory access time of expensive high-speed memory with a large memory size of less expensive lower speed. That's the main memory. So the goal, I would say the main goal here is to optimize or to increase the latency in order to let CPU always busy instead of staying idle. We also have as we said in the previous chapter, main memory is one of the large and slower, whereas cache, comparing to the main memory, is smaller and cache and smaller and fast memories. So normally cache contains a copy of a portion of main memory. This is where we are going to talk about how to map. It should be the next section. We'll have to map the main data from main memory to cache, because we know everything in main memory cannot go into the cache. Since cache is again, I would say smaller than main memory. So we have to have some algorithm to map it. And that's where the concept of locality, principle of locality comes in also. And we mentioned this earlier also. For example, if the processor attempt to read a word of memory, first thing will happen is that a check is made. That must, we have to check to determine if the word is in the cache. If it's not there, it's what we call a miss. If it's there, we have a hit. And if it's not in the level 3, we go to level 2, level 1, and we mention that. So the word is delivered to the processor if it's in the cache. If not, we go to the next cache to look until we get. So I would say that if not, then a block of main memory consists of some fixed number of words will be read into the cache. Then the word is delivered to the processor. Here we are assuming we check level 3, it's not there. Level 2 is not there. Level 1 is not there. Then we have to go to the cache. As we said today, we have automated system that always mapping data from main memory to cache to improve performance. Now we say because of the idea or the phenomena of or locality of reference principle. When a block of data is fetching, normally if it's fetching to a cache to satisfy a single memory reference, we will say that it's likely that there will be a future references to that same memory location, or at least to other location, but closer to it in the block, very close. So this gives us the idea of principles of locality again, in terms of spatial, temporal, in terms of time also. And as we said earlier, L2 cache always should be greater than L1 and also slower than L1. L3 cache should be greater than L2 but slower than L1, etc. So that would be the general idea. I think we mentioned this in our earlier slides. Now let's go through some of the terminology we need here. These are the elements of cache design. So first, the size. How many blocks can the cache hold? That's one question. We said about mapping function. So this is just, I'm going through the terminology here. So in the future lectures, we'll go through each one, especially the algorithms. We'll talk about them. So for example, here we say the mapping function is how it's a main memory block mapped to a cache line. Why we need mapping? Because the data in the memory is too large. All of them cannot go. Even if you join all the three caches together, they can't go in. So we have to know what data we have to. We want the data that is close, most likely the CPU is close to the CPU, most likely that's what the CPU wants. Because if we put data in level 1, 2, 3 cache, and all the data instruction, the function, the CPU don't need it, that means you have to go to the main memory. So all those caches are waste, not waste, but they can't do what they supposed. The goal that we wanted them to do, they can't do it. Yeah, so this is why we have to be careful about the mapping. So we also have what we call the replacement algorithm, which means which block to replace on a miss. Then we have a write policy, how are writes handled. We will go through all this in these lectures. Then we have what we call the line or the line size also, which means how many words are in a single cache line. And we'll go through all this. So a block normally will be the minimal unit of transfer. The minimal unit of transfer between what? The cache and main memory. So I'll say the term block again. Shows or no, refers, let's say refers to both to the unit of data transferred and also to the physical location in main memory or the cache. Then we have the inclusion policy. We're discussing the concept of inclusion, previous chapter. How do multiple levels of cache relate to, again, each other? So the next is cache addresses. And here we are talking about the CPU generate a memory address. So here, the cache memory, as we said earlier, is very small. Also high-speed storage that store frequently used data from main memory. And we also discussed the concepts of the principles of locality. And also, the goal here is to reduce the AMAT also. I would say that's the main goal of cache cache memory principles. Let me put it that way. So as we said earlier, here, CPU is the one that generates the memory address. And normally the address is split into three parts, so we should know what is stack. So we're going to use the word a lot. The word normally identifies the specific word or byte within it, and also you have a size. Then we have the set, we select specific set within a cache, and then the tag. Tag will be uniquely identify a block of main memory. As we mentioned earlier, we have both virtual and physical addresses. And caches can use either physical or virtual address. Let's wait for a few seconds. So again, tag will uniquely identify a memory block. And as we said, a set or index normally will point to a specific cache set or line also. Okay, so if no question, let's keep going. So next will be the cache size. Cache size depends. As we said earlier, L1 is smaller than L2, 2 is smaller than 3. If you have 4, then 3 will be smaller than 4. And the smaller one are more closer to the CPU, so L1 will be the fastest. Ideally, L1 will be somewhere between, let's say, around 32 kilobyte to 128 kilobyte. So wait for a few seconds if it's okay. So we may have a small cache, and also we may have large cache. Now the optimal size, as we said, is a balance between the speed, again, the cost, hit rate, which is often determined by specific applications also. Now, when it comes to the size, I would say that the trade here will be the size versus the latency, or with the cost or with the power consumption. Most likely, the smaller the size, the less power consumption. The smaller the size, the less overall cost, etc. And as we can see, large cache, slower access, but higher hit rate because it's bigger and it's more expensive. And we said about the optimal size already. So next we talk about the logical cache organization. So we talk about the direct map and also fully associative and set associative. So this is the concept of again mapping. Now, direct, to be very short here, direct map, that's why it's called direct map cache. Each memory block maps to exactly one line. Each memory block maps to one line. And it's very simple, also fast. And it has a very high conflict misses. Then we have, and here they mention each block of main memory maps to only one possible line in the cache. So very simple to implement, as we said, conflict misses. Then we have the fully associative. In short, I would say that any memory block can be placed in any cache line. in a cache line. So example, low comfort misses to expensive hardware. So you can see fully associated block can be placed in any well cache line. High hit rate, but complex and expensive to implement. Then the next one will be the set associative cache. Here we say that a cache divided into set, then each set holds multiple lines. So here we need a balance between complexity and also performance. And set associative is the most common approach today we have today. So direct map, the keyword is mapped to only one possible line in the cache. Each block of main memory maps to only one block. Now with a fully associative, we say that the block can be placed in anywhere or in any cache line, anywhere in the cache line. Then this is the most compromised set associative. Each block maps to a specific set, and it can be placed in anywhere or anywhere in there, any line within the set. And that's the most common one. So next week, we're going to end somewhere here. Next week, we'll go there. So this is the mapping algorithms. And next week, again, we'll go through each one. For example, we had a first in, first out, the most common one too. That's with the replacement. But again, we'll talk about this next week. Right now, I'm sure we have our 4:30 now. So I'll mark the slide down. We'll continue on slide 8 next week. So before we leave, I want to know if we have any question before I stop the record, especially about the project. Again, the project is due 2 weeks from now. So anytime you have a question, you can send an email to be okay. So, okay, almost quiet. So this means I'll stop the recording. I don't take any question.